In 2016, an outbreak of Zika virus struck the Americas, with millions of people infected and thousands of children with birth defects. Now, since then, we know that virus was circulating a full year prior to its first clinical detection. So could there have been a better way to keep an eye out on this disease and track it? I'm Philippe Selhorst. I'm a medical virologist, and for the last 16 years I've been working on many different viruses such as HIV, monkeypox, COVID obviously, and also mosquito-borne viruses. Now we're going to talk a little bit about how we can keep a close eye on these viruses so we can be better prepared for the next pandemic. The question of whether a new pandemic can occur is not a question of if, but rather a question of when. And there's still thousands of viruses out there in nature, and they're just waiting to make a jump to people. So it's very important that we see them coming, and we call that surveillance. So there are different types of surveillance. So the traditional surveillance is you go to the doctor's office and you're sick, and the doctor has to report that to the government, and the government reports it to the WHO. The problem with that type of surveillance is that it's very passive. That's why it's actually important to also do active surveillance, and you go look for the virus itself rather than waiting for the virus to come to us. If you go look for the virus itself, you're going to have to screen people that are not sick. And that's obviously quite difficult because people that are not sick, they don't want to get tested. So you need to find ways around it. As for example, we could screen blood donors for viruses, or more innovatively, we could test wastewater to see if viruses on a population level are present in that wastewater. But even that's still sort of not good enough. So we know a lot of these viruses, they come from animals or are transmitted by animals. We can, for example, test mosquitoes for Zika virus or dengue virus before they even infect or transmit it to people. So all of these next generation surveillance tools are made possible thanks to genomics. Now, what are genomics? Most people have heard of PCR, thanks to the COVID pandemic, and maybe also of DNA sequencing. And that's something they used to determine the different COVID variants. Now, what's the difference? So normal PCR just gives you a positive or a negative results. But with DNA sequencing, you can actually try to find the genetic code of that virus. And that is way more informative. If you have the genetic code of the virus, you can determine where the virus came from, when it arrived in the country, whether this is human-to-human transmission, whether the virus is mutating. And this is very important because it massively informs intervention strategies. So we know now, by doing genomics, that Zika was circulating a full year before the first detection clinically. So what could we have done if we knew that it was already circulating? We had a whole year. So we could have basically sprayed for mosquitoes in close to urban centers, exterminate these mosquito populations. We could have advised people not to get pregnant right before the wet season, and as such really diminish the scale of the outbreak. A second example could be more for Europe, when Zika gets imported into Europe with returning travelers. And that's usually not a big issue because that virus won't transmit locally. Why? Because the climate is too cold for the virus to grow in the mosquitoes, and the right mosquitoes are not always prevalent in Belgium. But this is rapidly changing with climate change, and we need to keep a close eye on that, and that's something that we're doing at ITN. Traditional vaccine development usually takes decades, and that's obviously too late. When a new virus causes a pandemic, you won't have anything to combat that virus. So there are two solutions to this problem. The first solution would be to develop universal vaccines, for example, against all flu strains. But we have been doing that for quite a while now, and we haven't been so successful yet. The second solution would be to focus on the development of fast and generic vaccine development platforms. And that's something that we have done successfully. The best example is the COVID pandemic, where decades of research in mRNA vaccines actually culminated in a very fast vaccine. And with very fast, I mean weeks. And the only reason why it took a year to develop was because we had to test it in people and manufacturing had to be ramped up. A way we can do that is potentially through artificial intelligence. You can have the computer predict which molecules will work against the virus, but also which molecules will work in the human body. And then a computer will actually present you with a smaller list of compounds to test for, and that will speed up the drug discovery massively. We're definitely better equipped now compared to the past, and that is thanks to COVID. But epidemic preparedness is so much more than biomedical interventions. We need a holistic approach. There needs to be open, transparent data sharing among scientists, all sorts of guidelines on when to close schools, when to close offices, when to close public transport, when to wear face masks, things like that. Thirdly, we need stocks of masks, vaccines, needles, therapeutics. And finally, the human component is also very important, because you can have a vaccine, but if people don't want to use it, then it's useless. So we need to study how we can communicate to people, how we can build trust with people, how we can get engagement from the community and things like that. Do you want to know how scientists track which diseases have the potential to become the next pandemic? Listen to our podcast.